there's a little bit more to wrap up the Lebesgue-dominated convergence theorem because of our assumption that the property is held everywhere instead of almost everywhere. But this little capture here that I've already written in here shows how you can deal with the almost everywhere condition if you have that for a whole sequence. And this is the way we would also show that the monotone convergence theorem and Fatou's lemma hold if you only have the conditions almost everywhere. I won't go back and do that for those because it's the same sort of technique. So in the general case where we only know that Fn in absolute values is less than or equal to G almost everywhere, and Fn converges to F almost everywhere, then what we'll do is peel off all the sets where those things fail. In other words, we'll define the sets Fn to be the set where absolute Fn exceeds G, and the set so that's for each n, and then F0 to be the set where Fn does not converge to F. We'll put those together, taking the union of all of those. Now each of those is a null set for each n, and since there's countably many of them, then put them all together, you get an L set. Well, then on the complement, E, everything works just as we assumed before, because on the complement, Fn does converge to F. So, in other words, I didn't write it in here, but we have Fn characteristic function of E converges to F characteristic function of E, and Fn characteristic function of E is less than or equal to G characteristic function of E. So those happen everywhere. Okay, those are true everywhere. We have squashed down to 0 the values on this null set where those would not have been true. So the theorem that we proved above holds for these functions now multiplied by the characteristic function of E. And also by 242 we know that we can say that the integral of Fn is just the integral on E of Fn, absolute Fn I should be saying, because the integral on F is 0, right? And so because the inequality holds on E, the integral of absolute Fn on E is less than or equal to the integral of G on E, which is finite, because the integral of G on E is integral of G, and that's assumed finite in the theorem. And F in absolute values is less than G on E, so the same thing happens when we integrate F over E. Oh, by the way, this is also the integral of F, isn't it? Right, in absolute values. So basically the functions, when multiplied by a characteristic function of E, as I said, satisfy the conditions of the version that we proved. And so now we can say that the integral of the absolute value of the difference of Fn and E is the same as the integral over E of that. With this is over all of x, the same as over E, which goes to 0. And in like fashion, using the same technique we used above, so does the integral of Fn go to integral of F. So that little technique just takes care of what happens with these sets of measure 0. You have to put them together. As I said, just like you would for the Lebesgue monotone convergence theorem, that works as well if the monotonicity only happens almost everywhere. Right, if the convergence only happens almost everywhere. So there's a nice corollary of the Lebesgue monotone convergence theorem, so I'm going to talk about that right now. And this corollary is, like we had with the monotone convergence theorem, an interchange of infinite series and the integral. So in this case here, we have a sequence now of integrable functions, whereas the earlier one had non-negative measurable, such that we have this additional condition the integral of, the sum of the absolute integrals is finite. The series whose terms are the integrals of absolute fn, that is finite, so it converges. That's enough then to imply that the series of the fn's, notice the series of the fn's doesn't occur in that box statement right here, but that is enough to show that the series of the fn's, so there's a convergent series of functions, pointwise convergence here, that is integral, and you can interchange the integral and the summation like so. So there's a couple of things to think about here. So let me go ahead and start the proof on this. So the proof here is of 244. So first we'll note the summation of absolute fn, like so, may converge or not, converges in 0 with infinity included, right? So it does converge in there, and hence is measurable. Since each partial sum is. Right? Partial sum is just a sum of measurable functions, a finite sum of measurable functions. So that is a measurable function. Also, by the corollary to the Lebesgue monotone convergence theorem, you know the number better than I do probably at this point. This says that the integral of that summation of the absolute values of the functions is equal to the summation of the integrals of the fn's and absolute values. So since those are non-negative measurable, we already have the theorem that says we can interchange infinite series and the integral. Okay, so that's from that previous statement. But we're told that this is finite. Now what does that tell you? Well, this is very interesting. What that says to us, since that's finite, is that this function here is finite almost everywhere. Yeah? All right. That's pretty cool. Thus, the summation of absolute fn is finite almost everywhere. What does that mean? That means it converges almost everywhere. So it converges pointwise almost everywhere. So this pointwise is a little awkward. I'm not going to even write it that way. Converges almost everywhere means that for each point in a set, it converges. That set has a complement that has measure 0. That right there says so it converges. Yeah. All right. So if we put, that means that's absolutely. Hence, the series fn converges almost everywhere. Okay, that converges almost everywhere. Because absolute convergence implies convergence. So for each point where this converges, so will this converge. And that is, if we write Sn is equal to the partial sum of the fk as k goes from 1 to n. So again, this is defined pointwise, right? For each x, that's how you would evaluate Sn. This is a convergent, this converges to S equal the infinite series, k equals 1 to infinity fk, almost everywhere. Okay, so now that's one of the conditions to apply the Lebesgue monotone or dominated convergence theorem. We have a sequence here, and this is the sequence that we're going to apply the theorem to. We have a sequence here that converges to a function almost everywhere. But what's the dominating function? Well, the dominating function is the series right here. That's going to be our dominating function g. That's going to fill the role of g. Now, absolute Sn, which is equal to the absolute value of the sum of the fk's, k goes from 1 to n, is less than or equal to summation absolute fk, k equals 1 to n, right? By the triangle inequality. Nothing fancy there except the triangle inequality for n terms, and that is certainly less than or equal to the entire series of absolute fk, k equals 1 to infinity, like so. That's almost everywhere, okay? That's happening almost everywhere, okay? In fact, that's everywhere. That's not almost everywhere. That's everywhere. There's nothing unusual about that, okay? But we have that right there. So now, thus, with g equal to the summation of the absolute fk's, I'll use the k now again since I've used it in this last expression. The Lebesgue dominating convergence theorem applies to imply that the integral of Sn goes to the integral of S. This is just the integral of the summation of the fk's. The integral of Sn is equal to the integral of the partial sum, which, because of our result in 242, is the sum of the integrals fk, k goes from 1 to n, but this limit, whose limit is, since we know it exists, right? We know the limit of the integrals exists, and that's just what this is, summation k equals 1 to infinity of the integral of the fk's. So the upshot of that then is that the limit of the Sn's is the integral of S, so those two things are equal. Okay, so it's a nice little corollary. It's useful, and we'll stop this clip right here.